welcome to the deep dive. Today we're tackling a really interesting conceptual puzzle, the tensor.
Right. It's this single mathematical idea, but it somehow sits at the heart of, well, two massive, very different fields.
Yeah, Einstein's general relativity on one side.
And modern artificial intelligence deep learning on the other.
It's pretty wild.
Yeah.
And the confusing part is that if you ask different experts,
A mathematician, a physicist, a computer scientist.
you get three different answers for what a tensor is. It seems incompatible.
So our mission, is to look at these perspectives and find the thread that ties them all together. Unify the definitions.
Okay, let's start simple then. Maybe the most intuitive way. Tensors as like a generalization.
Exactly. Think of it like those Russian dolls. You start with the simplest thing, a rank 0 tensor.
Which is just a scalar, right? A single number.
Yep. No indices needed, like the temperature reading right now. Just one value.
Okay, then rank 1.
That's your standard vector. It's got magnitude and direction. It needs one index to specify a component.
Got it. And rank 2.
That's a matrix. Now you need two indices. Think of it representing maybe stress in a material or how coordinates transform.
And then higher ranks just keep adding dimension.
Basically, yeah. Rank 3 needs 3 indices. Rank n needs n indices. It becomes a multi-dimensional array of numbers.
Okay, that multi-dimensional array idea. That sounds exactly like how AI folks talk about tensors.
It is. In frameworks like TensorFlow or PyTorch, when they say tensor, they mostly mean this multi-dimensional array as a data structure.
So it's less about the deep mathematical or physical meaning and more about practicality.
Precisely. The absolute key here is computational efficiency, that grid structure. It's perfect for computers.
Why perfect?
Because the data is laid out predictably in memory. GPUs, TPUs, they thrive on that. They can perform calculations on huge chunks of the array all at once in parallel.
So it's about speed, massive parallel processing.
Totally. Tensors are basically the universal language for feeding data into neural networks, holding the network's parameters, calculating gradients. Everything runs on tensors because it's fast.
Can you give us a specific, AI example?
Sure. Think about a simple color image. For a computer, that's immediately a rank 3 tensor.
Also.
You've got the height of the image, the width, and then the color channels, usually red, green, and blue. So 3 dimensions, rank 3.
Okay. Height, width, color. Makes sense.
And then when you train a model, you don't feed it one image at a time, right? You feed it a batch of images.
Right. For efficiency again.
Exactly. So you add another dimension for the batch size, and boom, you have your standard rank 4 tensor. That's like the bread and butter of computer vision models.
So the AI world really optimized this array concept for computation on fixed hardware, fixed coordinate systems in a way.
Yeah, you could say that.
But
Yeah.
physics isn't like that, is it? Physicists love changing coordinate systems. How does this fixed array idea survive that? How does it describe objective reality?
Now that's the beautiful part. For the physicist, a tensor isn't defined by the numbers in its array. It's defined by how those numbers change when you change the coordinate system.
Okay, unpack that. How it behaves under transformation.
Exactly. There's this fundamental principle in physics, general covariance. It basically says the laws of physics have to look the same no matter how you're observing them. Your coordinate system choice shouldn't change the underlying physics.
It needs to be objective.
Right. And tensors are the mathematical objects that have this built-in property. Their transformation rules guarantee this objectivity.
And this links back to Einstein.
Directly. He was struggling to formulate general relativity, and then he found this mathematical machinery developed by Ricci and Levi-Civita.
What was it called? Absolute differential calculus.
That's the one. It was exactly the language he needed. It allowed him to describe gravity not as a force, but as the curvature of space-time itself.
Which leads to the Einstein field equations.
Yes. Probably the most elegant equation in physics.
Yeah.
Fractal perfect.
Okay, so break that down. The Einstein tensor. That's the geometry part.
That's space-time curvature, yes. It tells you how space-time is warped, stretched, bent.
And the other side? The stress-energy tensor.
That's the stuff. Matter and energy. It describes the distribution of mass, energy, momentum, pressure, everything that causes space-time to curve.
So it connects the two.
Leading to that famous summary. Space-time tells matter how to move. Matter tells space-time how to curve. It's a dynamic interplay encoded in tensors.
Okay, I think I'm seeing the connection. The AI uses the array for computation.
In a fixed coordinate system, yes.
The physics demands that the laws work in any coordinate system using tensors defined by their transformation rules.
Right.
So What's the ultimate underlying thing? Is there a single definition that holds them together? The mathematician's view, maybe?
Exactly. The most fundamental definition is probably the multilinear map. That's the abstract, coordinate-independent object. It exists without reference to any specific basis or coordinate system.
Okay, the pure mathematical object.
Then the n-dimensional array that the AI person loves, that's just the components of that abstract map when you finally choose a coordinate system. It's one specific representation.
Ah, so the numbers do change if I change my perspective.
Hmm.
The array itself isn't the invariant thing.
Correct. The components change, but how they change is rigidly dictated by the transformation laws. That's the physics definition kicking in.
The rules.
The rules ensure that even though the numbers in the array change, they always describe the same underlying geometric object, the same physical reality, the same abstract multilinear map.
Wow. So the AI array, the physics transformation laws, the math abstraction, they're all just different ways of looking at the same core concept.
You got it. Data structure, physical law, abstract math, 3 facets of one reality.
That's actually a really neat reconciliation. Okay, before we wrap up, let's leave our listeners with something to chew on. You mentioned that stress-energy tensor.
Right, the source of gravity in Einstein's theory.
There's something really counterintuitive hidden in there compared to Newton, isn't there?
Oh, absolutely. In Newtonian physics, gravity is caused by mass. Simple. In relativity, it's the T-Dila component, the energy density, which includes mass energy, that's the main source.
Okay, it seems similar enough.
But it's not the only source. Other components of T22 T-Dilars, these represent pressure and stress within the matter.
Wait, pressure. Like the internal pressure of a star.
Exactly. That pressure, the outward push resisting gravitational collapse. It also acts as a source of gravity in general relativity.
That's wild. So the very forces holding something up against gravity create more gravity.
Yep. For incredibly dense objects like neutron stars, the immense internal pressure is a significant contributor to the space-time curvature around it. It's not just the mass, it's the internal dynamics, the stresses themselves that shape the geometry of the universe.
The universe cares about how much pressure you're under. Literally.
Literally. Something fascinating to think about.
Definitely. Okay, that's all the time we have for this deep dive. Thanks for joining us.